Okay. So, oh, ah, can everybody see this?
Yes, sir.
Yes.
Okay. So this is where we uh, left last time. So I said that if you take the isoclines, then there are only 4 ways in which these isoclines can intersect with each other. And I said that figure out what the dynamics of the isoclines will look like. And some of you actually ended up putting up the solutions on Zulip, but we'll work through the whole thing anyway. Okay. So let's take the first case. So we have N1 on this axis, we have N2 on this axis, and the first case was where, let's say, the isocline of species 1. So this is dN1 dt is equal to 0. Okay, and this is the isocline of species 2. So then this is going to be K1, this is going to be K1 by alpha 1 2, this is going to be K2, and this is going to be K2 by alpha 2 1, right? So what is going to be the dynamics? So this zone is below the isocline of both species, and therefore in this zone both species 1 and species 2, their populations are going to increase. So species 1 increasing, one can write it like this. Species 2 increasing, one can represent it like this. So the system, which is both N1 and N2 taken together, that will go in some direction like this. Now, in exactly how this vector looks will depend on what is the magnitude of this vector and what is the magnitude of this vector. But the basic point to note over here is that both N1 and N2 are going to increase in their size. Similarly, in this zone, you are above both isoclines. Therefore, N1 will decrease, N2 will decrease, and your resultant vector will be somewhat in this direction. Now, what's going to happen in this zone over here? In this zone, N1, we're still below the isocline of species 1. So N1 is going to increase in size, but we are above the isocline of species 2. So N2 is going to decrease, which means that we will go in this direction. Now, wherever you are in this zone, you will always get only this dynamics, which means that you are always being pushed towards this side. Now, when you are being pushed towards this side, you can either hit it at some point like this, anywhere over here. Then once you have done that, then species 2 has gone to extinction. You only have species 1 left in the population. Now, once you have species 1 left in the population, what will happen? Species 1 will go to, its carrying capacity, which is K1, which basically means that it will increase along this axis and it will hit K1. Even if it doesn't hit this directly, it will directly go and it will come over here. So essentially, whatever happens, species 2 will go extinct, and species 1 will be the only one which will be left. And this is, in the competition ecology literature, this is described by saying species 1 wins. Okay, so please note that over here the word wins explicitly means that 1 drives 2 to extinction, right? So this is our case 1. So let's think about case 2. So again we have N1, again we have N2, and again these two isoclines are there, except that now this is the isocline for species 2. So this is K2 and K2 by alpha 2 1, and this is my K1 and this is my K1 by alpha 1 2. Okay. So again, this zone is easy. You simply get this. This zone is easy. You simply get this. Here, you get the opposite, right? Because here you are above the isocline of species 1, which means that species 1 is going to go down, you are below the isocline of species 2, which means species 2 will go up, which now means that you are going to go in this direction, which means that end of the day the system will settle on K2, which means that species 1 will go extinct and species 2 will win. Okay, so this was our case 2. So now we come to case 3, where we have the two isoclines intersecting for the first time. So when they intersect, there are two ways in which they can intersect. So let's take the first one. So this is N1 in this direction, N2 in this direction, and let's say this is K1, and then this is going to be K1 by alpha 1 2, and this is K2, and this is K2 by alpha 2 1. Okay. Again, this part is easy. This is above both isoclines, so both of them decrease. This is again simple because this is below both isoclines, both of them increase like this. Okay. Now what's going to happen in this zone? This one, here we are still below the isocline of species 1, right? So 1 is going to increase, 1 is going to increase, but we are above the isocline of species 2, so 2 is going to decrease, which means we are going to go in this direction. Similarly, here it goes in the other way around. Okay, so which essentially means that wherever you are going to come towards, pulled towards these this point, and then if you end up on this side in this triangle, then species 2 will win, and if you end up on this side, then species 1 will win. Correct? Now what exactly happens here? What happens on this intersection point? So this intersection point is an equilibrium point, which means that at that intersection point, both 1 and 2 will coexist. However, this is an unstable coexistence. Why is it unstable? Because the moment there is some perturbation due to which you either end up in this triangle, then 2 will end up winning. If you end up in this triangle, 1 will end up winning. So this is the third case, is a unstable coexistence. Okay, so from this you should probably be able to guess what will be the case in the other one. So now this is K2, this is K2 by alpha 2 1, and this is K1, and this is K1 by alpha 1 2. Okay, so this one as usual is like this, this one as usual is like this. Here we are above K1, above the isocline of species 1, so species 1 is going to decrease, whereas we are below the isocline of species 2, so that is going to increase. So our net movement is going to be in this direction, whereas in this zone our net movement is going to be in this direction. So now this point, this intersection point, is again a coexistence point, but now this is a point of stable coexistence. Okay, and why am I calling it a stable coexistence point? That is because if there are minor perturbations, then this will come back to this coexistence point. Okay, so whichever way direction you perturb it, end of the day it will again come back right over here. ठीक है?
Sir, I had a question.
हाँ बोलो.
So in the graph 3, the point is in one direction it is stable, right? If you perturb it, towards the like how do I point it out? Like in one direction, if you perturb it, it's unstable. But if in a direction perpendicular to it you perturb, then it's stable, right?
No, 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 no. I think what you are trying to say is that if I perturb it in this direction, it's unstable. But if I perturb it in this direction, it's stable, right?
Yes, sir.
That's what, no, that is not true. Because when you perturb it in this direction, depending on how much you have perturbed, it doesn't come back to this stable point. It either goes in this direction. Okay, let me just clear the canvas. Okay. So what you are trying to say is that in this direction it is unstable, but in this direction if I perturb, then it will be stable. That is not the case, because when I perturb, it typically doesn't come back over here. When there is a perturbation, it goes either in this triangle or it goes into this triangle, and therefore it either goes here or it goes back here. Okay, it doesn't come back to this point, and therefore it's still unstable. Got it?
So what if I perturb it very slightly? Because when it for the first time came to that point, it came from somewhere, right? So
No. Typically, you shut your mic. So typically what happens is, it typically will never reach that point. Okay, the only way the system ends up going there in general is if you place it there. If you actually do a time evolution, most of the cases it will either go here or it will go here, and then it will come in, in these places.
okay.
The basin of attraction for that will be very, very, very small. Okay, anything else?
Sir, can I add something?
Bolo?
So what I did was, when I was solving this, I didn't just look at the trend of the direction. I looked at the trend of the magnitude also. So there are actually some cases. If so, in the case where it's dying out, where N2 is dying out, if the lines are further apart as you approach the point where N2 dies out, then the dynamics accelerates as you approach N2 dying out. But if they come towards, it actually decelerates. So
that is true. The closer you are to the equilibrium point, the slower it will become. That's what you're saying.
Exactly. And in the intersection cases, the stable equilibrium has an accelerating dynamics, and the unstable equilibrium has a decelerating dynamics, I think. The unstable has accelerating, sorry, because you're accelerating as you go towards the extinction, you accelerate. But when you come towards the stable point, you actually decelerate. So there's
yes, absolutely correct. Okay, I mean, let me show you guys all these things. Okay, is everybody done with this? Any other explanation needed over here? Otherwise, I'll take you guys to the simulations. Any one wants to make a comment or
sir,
bolo?
If the two lines overlap, then what will be the thing? The dynamics?
Very good question. So what you are saying is, if the two isoclines have overlapped, this, right, in some sense.
Yes.
Now think about it. If the two isoclines have overlapped, then that essentially means that they are indistinguishable from each other. They are the same species.
Oh, yeah, correct.
So, sorry to disturb.
Bolo?
I actually simulated this. So when I got the same isoclines, what happened was both the species went stable around their cave, like the caves.
Exactly. So if they're the same species, can you close your mic here? It's too much of echo. So essentially, what is happening over here is that both of them, for all practical purposes, are the same species, right? I mean, it's just one species. The entire ensemble is just functioning like one species.
Yes, sir.
So exactly what you are saying will happen, right?
But I think I had not every parameter was the same for both. It just so happened that the lines overlapped.
it
But
will
I'm
behave.
not sure. I just check that again.
The parameters are not the same. It will behave like that because see, this point over here, oh sorry, so this point over here, okay, is both k2 and k1 by alpha 1 2, correct?
Yes, sir.
That's the only way when that this side overlap will happen. And this point over here is both k1 and k1 by k2 by alpha 2 1.
Yes, sir.
That's the only way in which this overlap can happen. There is no other way. So basically, the two species are now behaving as if they are the same species, in the same way. Their parameters don't have to be the same. As long as they have these relationships, it will work out.
But it's like very fascinating because you can have very different dynamics for both individually, and if you just adjust these parameters, the Ks and alphas, even then they behave as the same population. So
And that is the first major thing that you guys should notice, that in this whole scenario, the R is completely missing. So when you guys are saying that they have very different dynamics, what you really mean are the R's, right?
yes, sir.
But you do observe that the R plays no role in terms of determining the final outcome of competition. The only thing that is playing a role is the K, the carrying capacity, and the way you are converting one species to another. So basically the equivalence functions or the equivalent scaling factors from one species to another. That's it.
Sir, does the R not play a role in reality or just in this model?
That's the big deal over here. Because intuitively speaking, that makes no sense. Intuitively speaking, you would assume that the species which has a greater R will be the one which will outcompete the other guys, right? But as far as this model is concerned, it doesn't bear out. In this model says that R completely goes out of the equation. End of the day, see, now this is where we come back to your acceleration, deceleration and all that. Those acceleration, deceleration, etc., those are all functions of R as well. Okay, they have to be.
Yes, of
But
course. You'll multiply them with R.
Exactly, no, you have to. Otherwise, how will you, do the model? But the problem is that what we are talking about over here is the ultimate outcome, in some sense, the asymptotic outcome. Okay, and those things are not a function of R, which, as I said, doesn't make too much of sense, except if you think in terms of the fact that the R and K in the model are independent, but in reality, R and K need not necessarily be independent. Do you guys remember at some point someone had asked me this question, that R and K, are they independent of each other or not? And I had said that the way the model is constructed versus the way the reality happens, they are two slightly different ballgames. In reality, they are not, but in the model they are. Okay.
In reality, R does not have an existence only, right? It's just a mathematical thing we have to model the system, right? Actually, there is no R, right? Or is there? Is R a physically measurable thing?
See, R is not a physically measurable thing, but R is a very close biological analog. Okay, because R in some sense is the number of babies that are going to be produced, or R is very closely related to the number of babies that are produced under unconstrained conditions. Okay, now the reason you have to get a model R is because in reality organisms will have a lot of variation in that. So you will have to end up taking some kind of an average over all of them, over their age and so on and so forth. And once you do all that, you get something that is very close to the model R. So the model R, yes, it is a model quantity, but it's not one of those defined, very artificial quantities. It has a reasonably close biological analog. Okay,
thank you.
This question about isn't R responsible for transition from one region to another, please note that that is in the discrete version of the model. Okay, we are, remember, doing the continuous logistic model over here, and we have taken over from that. In that context, you are not expected to get all those different dynamics. In that context, you will only get that nice approach to equilibrium. Okay. Okay.
Sir, in the cases wherein the isoclines are not intersecting, does it matter that if we like, suppose we are just hypothetically what extending the lines and see where they intersect. So suppose we do that. So does it matter if they intersect towards the side of N1 or N2?
No, but there is a point over here, na. By their very definition, N1 and N2 always need to be positive. So
Yes.
they can only exist in the first quadrant.
No. What I am asking is but the shape will change if it's like fatter in the bottom or narrower in the bottom, something like that. So will that change anything?
That will not have an effect. So basically, what you are asking is something like this. What you are asking is, I mean, let me know if I am correct. Suppose I have a case where the intersection is like this, they're looking roughly parallel, versus I have a case where the intersection, the isoclines are arranged something like this. They are still not intersecting, but there is a large gap over here. Is that what you are saying?
Yeah, and we can even invert that thing, that it's narrow in the bottom, and then
you can invert it like this.
So are these cases like equivalent?
They are all equivalent. Check for yourself that in all the cases, whichever is the guy which is below this isocline, this species will lose and this species will win.
Okay, I will.
Yeah, and see, that trivially follows from the analysis, right? Because whichever way we do these things, this zone is everybody increasing, this zone is everybody decreasing. In this zone, this guy has to increase and this guy has to decrease. It doesn't matter how the isoclines are arranged relative to each other. As long as they're not intersecting, the result is always going to be the same. Okay?
Right.
Okay. So, going to the Lotka-Volterra competition models. Can you guys see the popular screen, everybody?
Yes, sir.
Yes, sir.
Okay. So you can, I don't know if you can see the parameter values or not, but it doesn't really matter. I'm just taking whatever is given over here by default. And okay, can you guys see the trajectory? How it goes?
Yes.
The green trajectory. If you can't see it, just follow my cursor. Okay. So this is what the trajectory is like. So now what I'm going to do is I'm going to change the R values. So the R for the first one is 0.9. I'm going to make it 1.3, let's say. Okay. And now observe that the trajectory has changed. Can you see the new trajectory over here? Okay.
Yes, sir.
The trajectory has changed, but the outcome has not. And I can keep on doing this. I can, make this, I don't know, 2.5, the other one. And it's coming from a different side now. It's coming from a different side, but the outcome is still the same. So you can satisfy yourself by, through this stuff, that as long as, the isoclines are, in terms of their relationship with each other, that relationship remains the same. The outcome is always going to be the same. It doesn't matter whether you change your R's. It doesn't matter whether you change your K's, too much or anything. Okay. So we can play with this for a very long time. I'll leave that playing to you guys. But I'll strongly recommend that you guys do play with it, because there's a lot of stuff that you can learn over here. So for example, okay, I'll just talk about one thing. Now, let's get back to the whiteboard.
Sir, this is the one you just simulated. That is the case which is going to the equilibrium point, right?
That was the stable equilibrium point. Yes. Yes, I just took their default values, but you guys can put different values and see, how the case changes. I mean, here also I can change the different values, but okay, let me, I mean, that's exactly what I want to discuss with you guys. The one particular way of changing the things. Okay. So, yeah. So, suppose this is how the intersection is, and say this is K1 and this is K2 by alpha 21. Okay. So, okay. Now suppose this species 1 wants to become competitively superior to species 2. Okay. Now, what is it that is available for it to do, biologically speaking? See, in order for it to become superior, competitively superior to species 2, what is it has to do is to drive species 2 to extinction as much as it can. Now, the way to do that is for species 1 to extend, is to basically make sure that its isocline goes above the isocline of species 2, correct? Something like what this line I am drawing.
Yes.
Now, what is the way in which species 1 can do that? The simplest way, yes, exactly. Increase its carrying capacity, increase its K, correct? Because there is nothing else that species 1 can do which will keep this line straight and yet make it competitively superior to this one. Agreed?
Yes.
So, do you guys remember at some point we were discussing two terms, R selected and K selected populations, right? R selection and K selection. And we were saying that when you have increased, or when you have selection for increased K, then you have selection for greater competitive ability, right? This is the backdrop in which you get that. Okay, it is from this Lotka-Volterra equation and Lotka-Volterra competition equation, and the fact that this puts the constraint that this has got to be a straight line. In the context of this model, the only way for a species to become more competitive is to increase its K and nothing else. However, if you now think outside the model, if you now think outside the box, can you increase the competitive ability without changing K?
By changing R.
अरे आर तो है ही नहीं यार इस पूरे गेम में.
Sir, if you can change alpha.
Yeah.
Exactly.
If you change alpha, yes, but think about it. If you are going to change alpha 1 2, then by changing alpha 1 2, what can you do? You can make this point go up or down.
Yes.
So how will you make sure that this is always above this isocline? How will you make sure that the isocline of 1 is always above the isocline of 2?
By increasing alpha to 1.
By increasing alpha to 1. So that is one possibility. Okay, by you increase this and then you go down over here. This is called alpha selection, where alpha selection, where you increase your competitive ability not by increasing K, but by increasing your actual those parameters, okay, the competition coefficients. That's one. Anything else that you can think of?
Sir, in a realistic situation, can't you just eat everything in one area and then go away somewhere else before you die? Like migrate.
Yeah, then basically what you are saying is that you are not even having a assembly of two species, right? वो थोड़ा ज़्यादा हो जाएगा. And that's what
Yeah.
locusts do, for example. But then the
Yeah,
entire,
exactly.
then you are going outside the competition framework itself. Okay, fine. That is a strategy, but let's still be within competition. A very simple way of doing it, see, as I said, is that this bit about increasing k is there if and only if you have to, let's say, this is there only if this line needs to be kept straight. Okay, suppose you don't keep this line straight, you basically curve it something like this. Curve it something like this, right? Then I mean, okay, it has to actually come like this, very close to k. Again, if you end up doing this, then you can actually go beyond this k. You can actually be above this isocline for almost the whole part of it without necessarily changing your k too much. Correct? Making this isocline not linear but some kind of a curve.
Okay.
Okay, that's one thing. Another thing, not necessarily for increasing the competitive ability. See, again, we are thinking that this isocline always has to be straight. But suppose you end up having an isocline, so the competitive abilities themselves are density dependent. Okay, so your alpha 1,2s and alpha 2,1s, they themselves change based on the density. If that happens, then you essentially no longer have a one continuous straight line. This isocline itself can have, varied shapes, whereby in some places it can be above and in other places it can be below, something of this kind, the general, some generic shape that I'm showing over here. Correct? The moment you have something like this, then again you might end up getting, I mean, it depends on which one is 1 here and which one is 2 here. You might end up getting some points over here which are locally stable. Locally stable means that as long as the perturbation is within a certain zone, it will come back here. But if the perturbation is beyond a certain zone, then it will go in to this or this one. Okay?
So if we look at the kind of population models we've studied, what kind of population model could give rise to this kind of competition? Like if I look at the Lotka-Volterra model, we basically made a correction using the alpha to the population model which we already have. In that case, it was a continuous logistic. There is discrete logistic, there is recur. What kind of model could I make a correction to with an alpha term that would give me this kind of nonlinear isocline?
Okay, that I'll have to think about. Okay.
Or is this just observational data and not model?
This right now, what I'm telling you is just observational. Okay. All I'm trying to say is that if you come out of this straitjacket of having the isocline as a line, okay, and if you come up with a formulation in which the isocline can be curves, then you can get much richer dynamics, and you can get local pockets of within the same thing. You can get coexistence for some values, some combinations of n1 and 2, and non-coexistence for other combinations of n1 and 2, and so on. So the reason
one interesting thing I don't understand is how would you ascertain what the isocline looks like? If I have a community of 2 or 3 species which are in competition with each other and they are evolving in this way, I can find the trajectory very easily. How will the isoclines, how will I construct?
Mathematically making the isocline is going to become difficult, but biologically it may not be that difficult, because essentially all we are saying is that those values of n1 and n2, those n1 and 2 combinations, or n1 n2 n3 combinations, where the growth rate is close to 0. Correct? So I can get the intersection points empirically, and then one has to figure out, looking at the trajectories, what will be the rough shape of the isocline near those growth rates. I won't be able to get it as cleanly as I got it from the Lotka
You need a
Volterra.
lot of data because it would have to sample like all the different sides, so you can figure out the shape from this side, that side. So
We
your
are- we are-
computer will have to go into all the different regimes.
We are going to talk about competition experiments right after this. So I'll show you what kind of data we have.
Okay.
Okay.
Sir, are these experiments done? I mean, do we get observations which actually lead to such plots? Even
I'll
Lotka
show you-
Volterra?
Lotka Volterra kind of plots you get all the time.
Okay.
Okay. Lotka Volterra का कोई issue नहीं है. The other things, see, there is a lot of complexity over here. Okay, I have not yet gone into the complexities.
Okay, sir.
First, understand the simplicities, then we'll go to the complexities. Okay. Anything else? Okay.
So another question, small. Can we actually measure the alpha values, like without resorting to the model?
No.
Not right.
No. That you cannot. There is no direct measurement for that.
Okay, sir.
Okay, I have just 4 minutes. What can I do in 4 minutes? No, okay. I think I will leave the class right here. If you guys have any further questions, then let me know, and then we'll. Okay, let me just at least show you guys the PPT. So this is the Lotka-Volterra equation, and this is what we discussed. Can you guys see the screen, the PPT?
Yes, sir.
Okay. So this is the stuff that we ended up getting. Okay. So what is the what would be the trajectory of the system that you guys can figure out from Populus? Okay. Now, what is the major message that we are getting from this model? The main message that we are getting is that out of the 4 conditions that we studied, 3 of them are predicting that one species will drive the other to extinction. Now, if you remember, we started this whole discussion with Gauss's competitive exclusion principle, and I said that there were other studies which led to similar results, and all that suggested the same thing. You have 2 things or 2 species competing, then one is going to drive the other to extinction, right? So with this, it looks like our model is at least qualitatively capturing some aspect of the empirical observation. Now the main question is, what's happening in real life? So in the next class, we are going to start with that question, and then we'll see some examples from both sides, and then we'll take it forward. Okay. So as far as the class is concerned, it's we are done for the day. Okay. Yeah, as you can see, the answer is it's complicated. Okay, anybody? Bolo Kaustubh.
Sir, I simulated a discretized version of the Lotka-Volterra equations also. So I couldn't find any major difference except the fact that when you have R's much greater than say 2 or 3, then you get those oscillatory dynamics. But the trajectories I don't think were very different in comparison with continuous model. I didn't do many simulations, just 2 or 3, but from that I couldn't see much of a difference. It's just like instead of a continuous curve, it was for low values of R at least, like 1.1 or 2 point something. It was not a continuous curve, just like points joined with lines, but it wasn't very different from the continuous Lotka-Volterra. But I'll do more simulations today. I haven't done many.
Yeah, the point is it will depend on which regime you are doing it in. Okay. So most interesting will be the analogous of the intersecting cases. Now I don't know how we will reach those values in the context of the discrete one, but Yeah, you know what? My gut feeling is also कि if you increase the R values to something like 3 or so, you are going to get some interesting bits over there. Because see, one thing that the Lotka Volterra as the logistic does is it by and large maintains the population size to a very consistent level. So there is not much that happens over there. But in the context of the discrete one, you are going to get very sharp oscillations on its own. And if you are getting very sharp oscillations on its own, that itself will end up having very peculiar effects on the competitive inhibition on the other species. So my gut feeling is that you are going to get pretty major differences. I'll be very surprised if for all values of R and all combinations of alpha 1 2 and alpha 2 1, you are getting the same thing.
So actually, I didn't try R in the range 3 to 4. I actually had very low values of R and then very high values, and because of that Python rounding off feature, I guess I didn't get those large oscillations. So I'll try a 3-4 range today.
हाँ एक बार करके देखो. Yeah.
Shouldn't that make it less persistent stable if you have those oscillations? If they're sharp oscillations, it may go off to extinction very easily.
Yes, but the point is, see, Python still rounds off after very large number of digits. Okay, so you guys are not going to do for R equal to 8 or R equal to 10 or something. As long as you are up to R equal to 3 to 4, your values will go to 0.0000 something, but it will not go to 0. Okay, so the rounding off problem should not be too extreme for R values up to 4 or so. Beyond that, yes, it will become extreme.
There are biologically very relevant cases where you have higher R's though, right? So you can't simulate them in Python.
See, the problem is that for exponential logistic model, if you have very high values of R, the population size becomes unreasonably high pretty soon. Okay, so I don't think you will get too high a value of R even in regular life. Okay, हाँ बोलो कौस्तुभ.
So what we can do is in Python, one of my friends suggested this. We can actually scale up all the values. So it's actually going to 0 for, let's say, if the value goes to 10 power minus 20, then Python will say it's 0. So what I can do is I can try scaling everything by 10 power 20. In that case, I think we'll get oscillations. But I'm not very sure. I haven't tried it out.
I am also not very sure, because scaling up everything by 10 to the power 20 means when you have high values of R, anyway, when you are on the higher side, you are in the range of 10 to the power 10, 10 to the power 30, 20, something like that. Now you are scaling up everything by 10 to the power 20, so your high values will go to 10 to the power 40 or so. See, Python has, limitations on both sides, right? It's not that it has only limitations on the lower side. So I am not sure if that will work.
Yeah, I will have to use long double and I don't know what else. How to overcome this? I tried actually.
It is not as big a problem as you are thinking it is. Okay, you're going to R equal to 8 and all. As I was telling Akash, most of the time it doesn't matter. You don't get that high values of R most of the time. So even C will have this problem. I don't know about Julia, but I'm pretty confident that even C will have the problem. It might have it at a different range, but it has to have. Yes, computation time is a different ballgame altogether.
Sir, this may be a little like way too late to be asking this question, but R is defined as the number of progeny produced, or the number of progeny who survive to adulthood, or the number who survive to reproduce in their own turn. Which one is it?
So question is in the context of what?
Just in these models, what do we take R to be? Because if we are using this R for the next generation, it should be those that survive to reproduce, right?
See, the problem is if you are defining it in terms of the model, okay, just one sec. Let me stop the recording so that everybody can leave. I mean, people who want to leave can leave. Good. So it